Good afternoon, everyone. Welcome to the third interactive session of Symmetry and Group Theory. Uh, so, today we will be discussing. We have already studied like how can we find different symmetry elements and operations in a particular molecule. But now we will be collectively finding all the symmetry operations in a molecule and then and uh, grouping them, and then we will classify them into a particular group, what we call as point group. So here we will be taking some molecules, and we will find out whether like a certain molecule falls into which point group, and we will also see simultaneously like which of the applications of these point group, that is in the dipole moment, like whether molecule is polar or non-polar, or whether a molecule is optically active, it is symmetric, disymmetric, or asymmetric. So these are some of the applications of finding out the point group in a particular molecule. So let us take some examples, and let's begin our lecture today. Firstly, I would like to revise the flow chart to find out the point group in a molecule, so that like we would like to I would like to brush up the flow chart so that it would be easier in the to find out the point group of a molecule in the examples we will be following. So let us revise it. So basically we will be taking a molecular structure, and then we will check first whether the molecule is linear. If it is linear, then we will find out whether it has inversion center. If yes, if inversion center is present in that linear molecule, then it falls under D infinite H point group. If it doesn't have inversion center, then it will have C infinite V point group. So if a molecule is not linear, then we will move ahead and we will check whether the molecule has two or more C3 axis of rotation. If yes, then again we will check whether it has two or more C5 axis of rotation. If yes, then we will check whether it has inversion center. If yes, then it will have IH, that is icosahedron point group. If not, then it will have I point group. If it doesn't have a two or more C5 axis of rotations, then we will again check whether it has two or more C4 axis of rotations. So this IH, icosahedron, these are these come under cubic point groups. So if we have two or more C4 axis of rotation, then we will again check inversion center. If inversion center is present, then it is octahedral point group, and if not, then that comes under O point group. And if we don't have two or more C4 axis of rotations, then we will check whether it has one or more sigma planes. If yes, Then we will check whether it has inversion center. If we have inversion center present, then it will come under TH point group. And if not, then it will come under tetrahedral point group. And if one or more sigma planes are not present, then it will come under T point group. So this is the first part. Now, in the case when we don't have two or more C3 axis of rotations. When we don't have two or more C3 axis of rotations, then we will check whether it has a proper axis of rotation or not. If yes, if it has a proper axis of rotation, then next we will identify which proper axis of rotation it has, identify Cn, and whether we have NC2 perpendicular to this Cn, that this Cn proper axis of rotation. If this condition is satisfied, we will check whether sigma h is present or not. If sigma h is present, then then it will come under DNH point group. Okay, and if the sigma h is not present, then it will come under. Then we will check sigma d, dihedral planes. If dihedral planes are present, then it will be DND point group, and it will have n sigma d planes in it. And if we don't have sigma d planes, just a minute. Then it will come under DN point group. Okay. But in case when we don't have this NC2 perpendicular to Cn, then we will again check sigma h. So if it has sigma h, then it will come under CNH point group, and it will have no sigma v in it. But if we don't have sigma h, then we will check vertical plane sigma v. If it is present, then it will have CNV. Then the point group is CNV. If it is not present, then we will again check S2N, and if S2N is present, then it will be S2N point group, and if not, then it will be simply CN point group. Okay, and here also we have another classification. If we do not have any proper axis of rotation, then we will check sigma whether we have any vertical planes. If yes, then it will simply CS point group. If we don't have sigma plane, that is any any of the plane in the molecule, then we'll check inversion center. If inversion center is present, then it will have CI point group, and if not, then it is simply C1 point group. That is, it will have only identity operator. So this was a revision of this flow chart that we will be using in the further molecules. Okay, so I would recommend that you when you are finding out a point group a certain molecule falls in, then you follow this flow chart strictly. It will help you in reducing the mistakes in finding out any operations or the right point group. So the chances of any mistakes will be highly reduced, and it will help you in like um, you will be able to like on while practicing the molecules with this flow chart, you will be able to remember it for a longer time, I would say. Okay, so and also the applications of these point groups, which is first is polarity. So I'm simply writing here the groups which has like uh, C1, CS, CN, CNV. These point groups have dipole moments. All other point groups have zero dipole moment, therefore they are non-polar. And in these two cases, dipole moment will be along principal axis of rotation. Sorry, principal axis of rotation. And the another application is to find out the optical activity of molecules. So here we have studied like when is a molecule symmetric. So we will have to check the presence of improper axis of rotation, SN, proper axis of rotation, CN, and optical activity. So this is symmetric, then disymmetric, symmetric. So when we have this improper axis of rotation present, and this proper axis of rotation may or may not be present, then the molecule will be inactive. That is, molecule will be symmetric and it will be therefore optically inactive. But when improper axis of rotation is absent and we have only proper axis of rotation present in the molecule, then the molecule will be active. And if both of them are absent, then our molecule will be called asymmetric and it will be again optically active. So these are the applications we will be looking into a molecule. Okay, so let us begin with some examples now. The first example is xenon OF4. So it will have this we can say square pyramidal kind of structure. Let me draw it more clearly. This double bond O will be present above the plane of this xenon and four fluorine atoms. So, firstly, we will check, as I told you, whether the molecule is linear or not. So, we can clearly see this molecule is not linear. So, do we have two or more C3 axis of rotation in this molecule? I can't see even one C3 axis of rotation in this molecule. Therefore, we can write here two or more C3 axis of rotations are not present. Then we will check which proper axis of rotation is present in the molecule, whether this molecule has a proper axis of rotation or not. We can see here we have a proper axis of rotation present. So which is C4 axis of rotation passing through this xenon atom and this oxygen atom. So we have C4 axis of rotation here. So next we will be moving. Which proper axis of rotation we have? We have C4 axis of rotation. And we have to check, do we have four C2 axis of rotations perpendicular to the C4? No, we don't have four C2 axis of rotations present in this molecule. I can see a C2 axis collinear with the C4 axis of rotation, but no four C2 axis of rotations which are perpendicular to this molecule. Okay, like perpendicular to fourfold axis of rotation, that is C4. So this is not present. Now we will check, do we have a horizontal plane in this molecule? So this is C4 axis of rotation, and the horizontal plane perpendicular to it is the plane which is having xenon and this four fluorine atoms on it. So when we do a reflection along this plane, we won't get an oxygen atom below this plane. So we don't have a horizontal plane here. Okay. Now we will move further. Do we have vertical planes here? Yes, we have vertical planes here. One is this vertical plane having fourfold axis of rotation on it and passing through this xenon atom and reflecting these, I would say F1, F2, F3, F4. So this plane is reflecting F1, F4 on one side and F2, F3, F2 and F3 on other side of this plane. So we have one sigma V and another sigma V is 1, which is again having this xenon and oxygen atom, that is C4 axis of rotation on it, but now this time this is it is bisecting, like it is reflecting F1 F2 on one side and F3 F4 on another side. So this is sigma V1 and this is sigma V2. uh, I can show it like in another way also, this plane, which will be more easier for you to visualize this way. Okay, so we have sigma V planes. Yes. And we have, since we have n is equal to 4, which is even, we can also conclude here that we will have 2 sigma v and 2 sigma d, that is 2 vertical planes and 2 dihedral planes here. So the point group we have here is finally C4V. So the point group is C4V. C4V. And what are the total operations here then? Here we have identity operator, we have C4 axis of rotation, and what are the operations being generated from this C4 axis of rotation? That is C41, C42, C43, and C44 is again identity operator. But this C42 is equivalent to C2 axis, that is C2 axis of rotation. So we have two operations generated from this fourfold axis of rotations. Then we have two sigma v planes, two dihedral planes. Okay, so we finally I'm writing it as E C41, C2, C43, 2 sigma v, 2 sigma t. Total we have 1, 2, 3, 4, 5, 8 operations. Now let us check the applications here, whether this molecule is polar or non-polar. So we have already seen that C4V, that is here we have C4V point group, which is CNV point group. So it will have dipole moment, that is this molecule will be polar and the dipole moment will be present along the principal axis of rotation, that is a C4 axis of rotation here. So molecule is polar and have dipole moment along C4 axis of rotation, which is the principal axis of rotation of this molecule, and this molecule is optically active or not. We don't have improper axis of rotation present in this molecule, but we do have proper axis of rotation present in this molecule. So this molecule is disymmetric. Molecule is disymmetric as it has a proper axis of rotation present, but not improper axis of rotation. Therefore, this molecule is optically active. So let us take another example. We will be taking an alene with even double bonds. Which has two atoms, proton and chlorine atom. This is this hydrogen atom and chlorine atom present in the plane of the molecule. Let me show it. and these two atoms present above the plane and below the plane of the board. This is above the plane and below the plane. So firstly, we will check whether the molecule is linear. No, the molecule is not linear because all the atoms like these two atoms are present out of plane. This H and this Cl. The molecule is clearly not linear. Then, do we have two or more C3 axis of rotation? We don't have we don't have any C3 axis of rotation in this molecule. So we will move ahead. This shows that it doesn't fall under a cubic point group. And this cubic point group contains all these octahedral, tetrahedral, icosahedron, T, O, these point groups. Okay, so which is not present in this molecule. So we will move ahead. Then, do we have a proper axis of rotation in this molecule? Yes, we have proper axis of rotation in this molecule, which is C2 axis of rotation. Okay, and we have to check, do we have two C2 axis of rotation in this molecule? So, so we have C2 axis of rotation passing through this central atom. Um, Please find it out, like visualize it. C2 axis of rotation is present in this molecule. Then we don't have other two C2 axis perpendicular to this C2. So we have only one C2 axis of rotation here. So this condition is not fulfilled. Then we will check whether it has a horizontal plane. No. So if this is the C2 axis here and the plane is the plane perpendicular to it doesn't have equivalent atoms on both sides of it. So we don't have horizontal plane present in this molecule. Then we will check vertical planes. Do we have vertical planes? No. Again, passing through this is one vertical plane if we take, and one is in the this molecular plane. So these two planes are not giving any reflections uh, of the atoms because we have different atoms present, that is H, one is hydrogen and one is chlorine. So we are not getting an equivalent configuration. So we don't have vertical planes here. Do we have improper axis, that fourfold improper axis of rotation here? For that, we have to check, do we have C4 axis of rotation and then sigma plane. So neither we have fourfold axis of rotation in this molecule, and neither we have this any plane perpendicular to it. So S4 improper axis of rotation is not present. So we have only C2 point group. So at the end we find out that the molecule comes under C2 point group. Okay, and we know therefore molecule is polar and molecule is optically active because it has a proper axis of rotation but not improper axis of rotation. Therefore, it is disymmetric. Okay. So, what are the total operations we found out in this molecule? Which were E, C2 axis of rotation. These were the only two operations present in this molecule. So, we have two operations for this molecule. C2 point group and two operations. Okay. So, let us look into another example, which is a trigonal bipyramidal geometry of uh, PBrCl4. Instead of PCl5, we have PBrCl4. One chlorine is substituted with one bromine. So the geometry will remain trigonal bipyramidal. Will look like this. Okay. So we will be checking whether the molecule is linear. No. The molecule has trigonal bipyramidal geometry. Do we have C3 axis of rotation? Yeah, we have one C3 axis of rotation, but not more than it. No. We have Cn, which is C3 axis of rotation only, which is along this. This Cl1, 3, 4, passing through PCl1 bromine. Okay, so we have C3 axis of rotation here, but do we have three C2 axis perpendicular to this C3 axis of rotation? No, we don't have C3 axis of uh, 3 C2 axis of rotation perpendicular to this C3. If we would have PCl5, then this condition would have been fulfilled. But here, since we have this bromine present, so we won't get an equivalent configuration with any C2 axis of rotation operation. So this condition is not fulfilled. So again, we will check. Do we have a horizontal plane? So, perpendicular to the C3 axis of rotation, we have this plane which will contain Cl2, Cl3, and Cl4. So, when we apply this operation, and it will reflect Cl on one side and bromine on other side. So, we are not getting an equivalent configuration. Therefore, we don't have a horizontal plane present. Okay. So we will be checking, do we have sigma V planes here? Yes, we have sigma V planes present here, this molecule. Yes. So, and we know when n is odd, we will have 3 sigma V planes. N is odd implies n sigma V planes, that is 3 sigma V planes in this case. Okay, so we have, therefore we have C3 point group present in this molecule. And what are the total operations then? We have identity operator, C3-1, C3-2. These are the two operations coming from threefold axis of rotation. Then 3 sigma V. So we have total 6 operations. And since the molecule falls under the CNV point group, so the molecule is polar. And optically active and disymmetric. So the next example is N2H2. So we will check again whether this molecule is linear. So the molecule doesn't look like it is. So the molecule is not linear. Then 2 or more C3 axis of rotation are not present. Okay. Do we have a proper axis of rotation? Just a minute. Let me check whether it's happening or not. So, which is the proper axis of rotation present here? We have C2 axis of rotation, but we don't have two C2 perpendicular to this C2 axis of rotation. We have only one C2 axis here. And do we have sigma H plane? This is the C2 axis, and this is the molecular plane, which is sigma H. So we have sigma H plane present here. So this is C2H point group. So the total operations present in this molecule are identity operator, C2 axis of rotation, sigma h, and I would like to give you some tricks, kind of concepts for this. If we have Cn plus n sigma h, that is for this CNH point group, if n is even, then I will be present. If n is odd, then I will be absent. And in these and in CNH point group, Sn will be present. Here, in this case, here we have n is equal to 2. So Sn is equal to S2. But S2 is equal to I. So we have this inversion center present in this molecule. Okay. So we have total 4 operations in this molecule. Similarly, you can solve this molecule C double bond C, that is uh, trans dichloroethene. It has C2H point group. Now we will check the application. This molecule is non-polar eh, because we have both proper axis of rotation and horizontal plane in this molecule. And this molecule is symmetric. As we have both improper axis of rotation and proper axis of rotation present in the molecule. Therefore, this molecule is optically inactive. The next molecule is okay. So we will start with whether the molecule is linear. Clearly, it is not linear. Do we have two or more C3 axis of rotation? No, we don't have any C3 axis of rotation in this molecule. Do we have proper axis of rotation in this molecule? Yes, we have C4 axis of rotation, which is present here, perpendicular to the plane of the board. And do we have 4 C2 axis of rotation perpendicular to this C4? No, we don't have C2 axis of rotation in this molecule. No. So do we have horizontal plane here? Yes, molecular plane, that is plane of the board. So the molecule comes under C4H point group. Okay. So what are the total operations we have? We have identity operator, then the operations from this fourfold axis of rotations are C41, C42, C43. C44 is identity operator, and this is equivalent to C2 axis of rotation. This is equivalent to identity operator. Then we have sigma h, horizontal plane. And then we have S41, S42, S43. S44 is again identity operator, and this S42 is equivalent to S2, which is equivalent to identity operator. So the operations we have are identity operator, C41, C2, C43, um, sigma h, S41, identity operator, sorry, inversion center, S43. These are the operations we have. So total we have 2, 3, 4, 5, 6, 7, 8 operations in the molecule. And since it comes under this CNH point group, it has CN proper like C4 axis of rotation and horizontal plane. So the molecule is non-polar. And the molecule has a proper axis of rotation and improper axis of rotation. Both are present here. So the molecule is symmetric and optically inactive. Okay, so the next example is again an alene with even double bonds. But this time we have four. So the um, axial atoms are hydrogen this time. So this is even double bond alene with double. Okay. Now we will check whether the molecule is linear. No, the molecule is not linear. These two protons are out of plane. So do we have two or more C3 axis of rotation? No, we don't have any C3 axis of rotation here. Do we have a proper axis of rotation in this molecule? Yes, we have a C2 axis of rotation. So we have one C2 axis of rotation like this, then this C2 axis of rotation, one perpendicular to the another place. So we have two C2 axis of rotation. Uh, sorry, we have principal axis of rotation C2 and two C2 axis of rotation perpendicular to this principal C2 axis of rotation. So then we will check whether it has horizontal plane. So yes, it has horizontal plane. Sorry, so it doesn't have an horizontal plane. Because if you see, this is the principal axis of rotation, and if you draw this plane perpendicular to it like this, then you have two protons which are in the plane of the board and two protons out of the plane. So you're not getting an equivalent configuration. So we don't have an horizontal plane here. So we will check dihedral planes. We can represent this molecule like this also. Okay, so we have C2 axis of rotation like this, and we have dihedral planes like this. So these are sigma d. So we have two dihedral planes. So the point group is therefore 2D point group. So what are the total operations we have in this molecule? We have identity operator, C2 axis of rotation, and then two C2 axis of rotation perpendicular to it. We have two sigma D planes, and for here in the case of D and D point group, we always have, let me tell you this, in case of D and D point group, S2N will be present. And if N is even, then I will be absent. And if N is odd, then inverse center will be present. So if we see here, we have S2N will be S4 in this case because N is 2. So S41, S42 and S43. So this S42 is equivalent to S2, which is again equivalent to inversion center. But as we have said, for in case of even N, we will not have inversion center, so this will not be present. So we will get only two operations from this fourfold improper axis of rotation. So the final operations will be E C2 to C2 dash to sigma D SO1 and SO3. So there are total 8 operations. Okay. So the next example is staggered ethane. So how do you draw it in Sawhorse projection? This. Okay. So I'll represent it in Newman projection this way. H1, H2, S3, then S6, H4, which is kind of, so this is the projection we are getting. So we will again find out whether so the molecule is not linear. Do we have C3 axis of rotation here? Yes, we have C3 axis of rotation perpendicular to the plane of the board. But we have only one C3 axis of rotation, so this condition is again not satisfied. Then yes, we have proper axis of rotation, that is C3 axis of rotation. Do we have three C2 axes perpendicular to this C3? Yes, we have. So, which are, these are the C2 axis of rotation. And okay, so uh, removing it from here to avoid any confusion. Okay, so this is one C2 axis of rotation. Okay, and then we will check whether we have a dihedral plane in the molecule, sorry, a horizontal plane in the molecule. So we don't have an horizontal plane because this is C3 axis of rotation perpendicular to the board. So when you take a plane, this molecular plane, so it will not reflect any proton with respect to S2 uh, and similarly with respect to S3 equivalent to it. So we won't get an equivalent configuration. So then we will check dihedral plane. So do we have a dihedral plane in the molecule? Yes, we have a vertical plane containing the principal axis of rotation and bisecting two C2 axis of rotations. So we have dihedral planes. So the point group will be D3D point group. So D3D point group is present. So what are the total operations present in the molecule? Identity operator, C31, C32, then three C2 axis of rotation, three dihedral planes, uh, S61, S62, which is equivalent to C3, S63, which is equivalent to S2, which is equivalent to I, and since we have N is equal to O, so we will have inversion center present in this molecule. Then S64. So you must have observed, like if we follow this flow chart properly, then we can even find any operation we couldn't visualize easily. So if we are going to miss on any of the operations, so we can easily find out with respect to this flow chart. So please practice it carefully. It will be very beneficial for you and in the applications and other parts of this course. So the final operations are, I'm listing them again. 6, 5 and inversion center. So we have total, how many operations we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. We have total 12 operations. This I have mentioned mistaken, the mistake here. It will be S65 inversion center. So we have total 12 operations in this molecule. So these were some of the examples. Let us take a 5-minute break. If you have any questions, any doubts in these examples, then you can ask me. Okay. So let us solve other examples. So this is tri-substituted phenyl ring. So we'll find out the point group in this molecule. So the molecule is not leaking here. Do we have C3 axis of rotation here? Yes, we have C3 axis of rotation, but we don't have uh, more than one C3 axis of rotation. So we have C3 axis of rotation, which is present this this center of the molecule. Right. So it is present at the center of this molecule and coming out of the it is coming perpendicular to the plane of the board. So C3 axis of rotation. Do we have three C2 axis of rotation perpendicular to it? Yes. Yes. There are C2. We have perpendicular to C3. Okay. So this condition is fulfilled. Then do we have horizontal plane? Yes, we have horizontal plane. That is the molecular plane in this case. So the point group is TNH point group. And we know for port N, we have N sigma V. And we have here N is equal to C3, N is equal to 3. So we will have 3 sigma V. And for even N, we will have N by 2 sigma V and N by 2 sigma D. So the point group here is, it will be D3H point group. Is present. Okay. So in case of DNH point group, we will have SN present in the molecule. Okay. If N is even, then I will be present, and if N is odd, I will be absent. So this molecule has N is equal to 3 odd, so inversion center will not be present in the molecule. So what are the total operations which will be present in the molecule? We will have identity operator, we will have C31, C32, then we will have 3C2, 3 sigma V, S31, S3. What are the total operations we have in this molecule? We will have 3, 6, 9, and we have sigma H also. So we will have total 12 operations. Okay, and the molecule will be is non-polar. And molecule is optically inactive since it is symmetric due to presence of proper and improper axis of rotation. Okay. So similarly, you can solve other examples similar to this molecule, like uh, I'm writing it as similar examples. So you can solve BF3. It will also have D3H point group, and you can also find it out in this N3 P3Cl6. So it will have this geometry. Okay, so you can find out the point group in this. Like you can follow the flow chart. It will have D3H point group. I've shown a similar example here. Also, you can check it in this molecule. So these molecules have D3H point group. One more example is there, uh, which is bicyclo 1,1 pentane. So you can represent it like this to properly visualize the point groups. So this will also have D3H point group. So Uh, so Naveen, you have joined recently. So we were discussing some molecules and we were finding out the point groups in these molecules. So do you have any doubts? Uh,
No, ma'am, no, ma'am.
okay. So let us take more examples. So we have taken. We will be taking this bicyclo 110 butane, which is equivalent to this. It can be represented as, so we will be labeling these protons. So let us find out the point group here. Since the molecule is not linear, and do we have two or more C3 axis of rotations? No, we don't have any C3 axis of rotation in this molecule. So do we have a proper axis of rotation in the molecule? Yes, which is C2 axis of rotation, which will be passing through the center of this bond and perpendicular to the board. So this is C2 axis of rotation. But do we have two C2 axis of rotation perpendicular to this? No. Now we will be checking, do we have a horizontal plane here? No, we don't have an horizontal plane. But do we have sigma v planes here? Yes, we have two sigma v planes passing through this principal axis of rotation, bisecting the molecule like this and like this. So we have two sigma v planes. So the point group is C2V point group. Therefore, the point group is C2V. So the molecule is polar and optically active. Since we have proper axis of rotation but not improper axis of rotation, the total operations in the molecule are E C2 to sigma V. So we have four operations in the molecule. Okay. So there are some derivatives of PCl5. I'm writing here. Please find out the point groups for each of them. Although I'm writing in which point group they fall in, they belong to. Okay, but you have to practice it yourself. So PCl5 comes under C3V point group. Sorry, this comes under T3H point group. With total operations of E C31. Since we have already solved in previous lectures how to find the symmetry elements and operations in this molecule, so I'm writing it directly. We will have 3C2, 3 sigma V, sigma H, S31, S3, 2. So the total operations are 2, 3. There are 12 operations in this molecule. But if we substitute it with one different atom, like we have earlier solved PCl4Br, so we will get C3V point group. It has C3V point group. And if we substitute two chlorine atoms with bromine atoms, what will be the point group? So it will have C2V point group. if we So here we substituted the equatorial chlorine atoms, but if we substitute the axial ones, so then you will get D3H point group. And if you substitute it like one axial atom, one axial chlorine atom, and one equatorial chlorine atom, you will get CS point group. That is, you will have only one sigma plane and one identity operation in this point group. So please practice these four molecules yourself and find out how you reach these point groups. Okay. Few other examples are CTCl4. So it will have D4H point group. And if you take this molecule, these are examples of D4H point group. Now the benzene ring, it will have D6H point group. It will have T5H point. So there are other examples similar to this. for D and D point group, which I am writing here. So D and D point group will have proper axis of rotation, this NC2 and N sigma V, S2M, and if N is equal to E1, then I will be absent, and if N is equal to 4, I will be present in these cases. So what are the examples for this? This is staggered ethane. Will have D3 D point group. It will have D2 D point group. If you take a cyclo, this will have D4 D point group. Uh, this is ferrocene. You have molecule. So I have already solved similar examples above. So these are I'm giving you just for practice. So these were the examples. These like ferrocene and all these metallocenes. These were staggered metallocenes. Okay. So when we have eclipsed metallocenes, like both of the rings are eclipsed, like stacked on one of stacked like on each other. Then we will have DNH point groups. So if you have any doubts, you can ask me, or I'll be writing more examples for practice. So let us take an example of TN point group. So we'll represent is like this. So following the flow chart, molecule is not linear. Do we have two C3 axis of rotation, like two or more C3 axis of rotation in the molecule? No, we have only one C3 axis of rotation. So we have proper axis of rotation, which is C3 axis of rotation. Second, do we have three C2 axis of rotation perpendicular to this threefold axis of rotation? Yes, we have. Like it will be represented like this. We have three C2 axis of rotation perpendicular to the principal axis of rotation. Then do we have sigma h horizontal plane? No, we don't have an horizontal plane because C3 axis of rotation is perpendicular to the plane of the board, And if we draw a horizontal plane, which is a molecular plane here, we won't get an equivalent configuration in that case. So we don't have sigma h. But do we have a dihedral plane? So if you see here, we have this plane, sigma d. This is the sigma d plane present in the molecule. So we have dihedral plane. So the point group will be D3D. Sorry, D3. Actually, we don't. Sorry, I did a mistake. Yeah. So we don't have a sigma dihedral plane here. That's why we have D3 point group. So what are the total operations? We have identity operator, then C31, C32, 3C2. So we have total 6 operations. And since we have here more than one proper axis, one since we have more than one proper axis of rotation in this case, so the molecule is non-polar and the dipole moment will be 0. Molecule is optically active since it has proper axis of rotation but not improper axis of rotation. So let us summarize the point groups here. If we have proper axis of rotation and n C2 perpendicular to it, n vertical planes and horizontal plane, then we will have D NH point group. If we have proper axis of rotation and NC2 perpendicular to it, N sigma V but not horizontal plane, then the molecule will have T and D point group. If we have like proper axis of rotation and NC2 perpendicular to it, then the molecule will have DN point group. So in the cases where we have more than one proper axis of rotations, there we will get dihedral groups, dihedral point groups. And when we have Cn, proper axis of rotation, and n vertical planes, then we will have CNV point group. And if we have Cn, that is proper axis of rotation along with the horizontal plane, then we will have CNH point group. And if we have Cn only, that is proper axis of rotation only, then the molecule will have Cn point group. And if we have only sigma, that is only plane, then the molecule will have Cs point group. So these were some examples where we found out the point groups in the molecules. So you can practice and you can write to me if you have any doubts. Okay, and we can also discuss in the last class. Sorry, in the next class. So this is it for today. Thank you very much.